we're recording. All right, how did homework 2.2 go? Was that bad or was it okay? I mean, hopefully it would, like...
That's okay. I guess we'll see how it is.
Each of the homework, like we're starting to very slowly sort of like ratchet it up in things that we handle. I mean, we're already, I know we're still doing support reactions, but we're already just a tad off of the beaten path and stuff we did in undergraduate statics and whatnot. So we're rocking and rolling in terms of content. We're going to have 2 more lectures devoted to support reactions. And if you notice, each of my lectures, I try and focus on a given thing. Like this is what we're talking about today, so that we have sort of a closed coverage of a particular concept. And so today's topic is basically that of concentrated moments. Okay. Now with inclined loads, we had inclined loads that were applied to the structure, actual external loads, and then we had support reactions that were inclined. Well, the same thing here. We're going to have concentrated moments that are applied to the structure, and then we're going to have concentrated moment reactions. And so we have concentrated moment reactions whenever we have fixed support conditions. So just make sure that you're good with that. Okay, I graded homework 2.1. Largely everybody did a really good job. I would say if there's any big pieces of advice, I would just make sure that you're dotting your I's and crossing your T's on accounting for all of the forces and whatnot when you, some moments, and that you just pay attention to where you locate the centroid of triangular loads and things like that. But other than that, I mean, broadly, everybody understood what was going on. So homework 2.2 was due today, and then homework 2.3 is assigned today. That's a typo because it says due Wednesday, but it's due Friday. I'm going to fix that right now. And then we're going to have a homework assignment that is assigned on Friday, but it's due Wednesday because of the holiday. So I won't have anything due on the holiday. I don't operate that way. So thank you. You are quite welcome. It's a holiday. Take a break. So okay, sound good? All right. So let's talk about concentrated moments. And I'll tell you that the homework assignment that I assigned will probably be a tad shorter than the one you just did. Sorry. This one will be a tad shorter than the one you did the last one. The 2.4, the one that'll be assigned over the holiday weekend, it will be, the problem will be a little bit more involved, but you'll have a lot more time to do it. So, and I think I'm only giving you one problem on that one, not 2. Okay, so let's look at concentrated moments, and we're also going to extend that discussion into cantilevered beams and fixed reactions. Okay, so I want to talk about, just make sure that we're all clear on what we can handle so far. And I say so far, we've assessed beams subjected to. But that statement's a little deceptive because you had homework assignments where they've been frames. I could have given you homework assignments with trusses. Right now, what the actual structure looks like doesn't really matter all that much. What we're looking at now are just what are the support conditions and the reactions at those support conditions required to achieve equilibrium for the entire structure. So the structure could be a beam, a truss, a frame. It could be anything. It doesn't really matter. Later on, what the structure actually is will matter. But so far, we've assessed structures that are subjected to concentrated loads, distributed loads that are both uniformly distributed and linearly distributed, and we've also looked at structures subjected to inclined loads. As for the boundary conditions that we've assessed, we've looked at simple boundary conditions up until this point. So those are pin boundary conditions and roller boundary conditions. And for the roller supports, we're either looking at perpendicular supports or supports that have an incline. So already just from 2 lectures, we've handled quite a bit. We're not done because we've got a couple more things we need to assess, but so far we've done quite a bit just in these couple lectures. What I want to talk about now are concentrated moments. Okay, concentrated moments really in the real world come from 2 places. Okay, so the first comes from torsion or from you have some element that's framing into a beam or column that is generating some sort of twisting aspect. So for example, if I was looking at this scenario right here on the top right. So I have a floor beam that's subjected to load. Let's say this is a cantilever. Let's say, this is a floor beam that's supporting a cantilever deck outside of a building. So this floor beam would cause sort of a twisting on this spandrel. And so if I'm looking at the column is seeing a concentrated moment. Like imagine here's the column and I'm taking it, I'm just sort of twisting it right at one point. That's what the column is seeing in that scenario. And so that's different than an applied force or applied distributed load, an actual concentrated moment applied at a given point. We need to learn how to deal with that. Concentrated moments also come in the form of reactions when we deal with fixed supports. Fixed supports have three reactions. They have a vertical load, a horizontal load, and then a concentrated moment reaction. A simple example of how that would exist in the real world is if you ever have a ruler or some sort of like ruler, or I hear some clanking around, or like a drafting triangle or anything like that. Grip the end of it and then take your finger on the other end and push it. Okay, you find that your finger is not only having to like hold it up from translation, but it's kind of having to like prevent it from rotating. So it's almost like you're taking that end of the ruler and sort of doing that to it. So that is a concentrated moment reaction at that fixed support. Now, in addition to concentrated moments actually physically existing in the real world on structures, they will also prove to be a necessary analytical tool. So later on, so right now in this class, what we're dealing with is what I would call the force side of structural analysis. Here's a system, we apply some loads to it. What are the resulting forces? Reactions, internal forces and trusses, etc., etc. Later on, we're going to look at the other end of it, which are the deformations. Okay, when you take a structure and you apply load to it, it will deform. I don't care what it's made out of, it deforms. And so we as structural engineers need to be able to compute those deformations. Now, one of the most robust methods of doing that is what's called the method of virtual work, or the unit load method. And in that method, you actually do two separate structural analyses. You do one analysis with the loads as they are on the structure, and then another analysis where you take all those loads off and you put a single force where you're interested in finding deflection. So if you have a beam and you want to find the deflection right there, you put a single load right there. And a single force will give you the amount of translation. A single concentrated moment will give you the amount of rotation, how much the structure rotates, or what's the slope at a given point. And so we are going to deal with some of these concepts not just as representations of what's going on in the real world, but as analytical tools for computing other responses. So that's going to be a theme a little bit later. Now, what we're going to do today is we're going to do two problems. I'm going to give you this problem here first. This is going to be a support reactions problem using the same support conditions as before, but with a concentrated moment. But then we're going to talk about cantilever beams. I do want to mention right now a couple of quick things about cantilever beams. They are incredibly common in structural applications. You will find them all over the place. Cantilever support conditions tend to arise not just with beams, but with columns as well. So for example, if I'm looking at that light pole right there on the other side of 3rd Avenue, that light pole is substantially, buried some distance in the ground. So if we're looking at the component of the light pole that is above the ground, we can pretty much assume that support condition is fixed, because not only will that support condition between the ground and the light pole withstand translation, like the light pole literally isn't moving to the left or right or up or down, but that support condition, I think we can assume to resist rotation as well. But in the land of beams, you find them for balconies, awnings, things like that. One other component that might be a little deceptive to think of as a cantilever beam is a support condition for a bridge. So for example, if you have a hammer pier type situation, we can look at, let me put the pen on here. We can look at this part right here. I might have to use the actual part here. But if we look right here, So, and we look at this left end of the beam, we can sort of treat this component of the pier as a cantilever beam, because we can treat this as the fixed support, and it's getting all that load from the support reactions from the bridge. And so part of the challenge is detailing the amount of reinforcement to withstand that bending moment that you get right there. And there's a ton of reinforcement right here across that pier location. So those are some real world examples of that. So we're going to have two problems. One's a support reactions problem and one's a concentrated moment problem. So let's get into these. All right. So let me pull the first one up. So here's the problem. We're going to compute the support reactions of this overhanging beam. And notice how what I'm trying to do is I'm trying to incorporate the stuff that we've dealt with in previous lectures, but again, ratcheting it up just a little bit, okay? Obviously, we see what's new about this problem. That's that 20-foot kip concentrated moment. But we do see a lot of stuff that we've dealt with before. We have a overhanging beam, so we have simple boundary conditions. We have a distributed load, concentrated load, so a lot of familiar stuff as well. So we're sort of, again, slowly getting into deeper ends of the pool, as it were. I'll give you all a sec to copy that now. Everybody good? I'm going to add some stuff to this. Okay, so first off, let's deal with this distributed load. So I have 3 kips per foot extended over a distance of 10 feet. So I can collapse that into a single load. Oh. Maybe I have to use that. Yeah, I think so. 30 kips, okay? And this distance right here is what? Make sure everybody's paying attention somewhere. 5 feet. Okay. Now I'm going to go ahead and indicate my unknown reactions as well. Just so you know, I don't think I've started doing this yet, but sometimes on my homework assignments, what I'll do for the reactions is I'll draw them with a little tick mark in them. So like here's BY, and I'll draw a little tick mark on them. I usually kind of do that to indicate those are my unknowns at the beginning of the problem. So if you see me doing that on a homework problem, you go, why did he put a little tick mark on his reactions? That's why. Especially because if I'm doing it in pencil, then I don't have the luxury of all the colors and whatnot. I guess I could get some colored pencils, but I haven't done that yet. All right, so that's BY, that's AY, that's AX, so we'll put a little tick mark on that. Okay. All right, and I think that's pretty much it. Now, this 20-foot kips, the big point I want to get across is that it's a moment. It's not a force, it's a moment. And if you keep that in your head, then I think that how we handle this is going to be extremely simple, okay? So first off, we have 3 reactions. We have 3 equations of equilibrium. So let's handle those. Let's start off with the sum of forces in the x direction equals 0. Are there any forces being applied to the left or right? No. And this moment does not count. Again, I'm asking about the sum of forces in the x direction. That's not a force. That's a moment. So if there are no forces being applied laterally to this system, AX is 0. No different than what we've done in previous problems. Just because there's a moment there doesn't change anything. This is the sum of forces in the x direction. There are no forces being applied in the x direction. So AX is 0. Okay. Now, I'm going to treat this like I've done problems up until this point. We're going to sum moments at A to determine the reaction at B. Okay? So, let's handle this one step at a time. Summing moments at A. Do I consider AX? No. Do I consider AY? No. Do I consider this 30 kips? Yes. 30 kips is contributing moment on this side, right? And what's the moment arm? 5 feet. So over here, 30 kips times 5 feet. What about the BY? Does that contribute moment? Yes. Contributes moment this way times the moment arm of 25 feet. Here we go. Now, the kicker of this problem, this right here. So I guess the first question is, does it contribute moment? Does it generate moment at A? Yeah, it's a moment. All right? Which side of the table does it belong on? The left or the right? Belongs on the left, right? It's literally a moment. Now, what's the moment arm? The answer is, there isn't one. What are we doing here? We are summing moments. That's a moment. Just put 20. No moment arm, no distance. It's a moment. We're summing moments. So you just put 20. No distance, just 20. That's it. That's the only complication. Now, am I done or did I forget something? The 10 kips. I got to handle that 10 kips. It's going to generate moment at A. What's the moment arm? There we go. That's it. That's the only complication, right? So 30 times 5 is 150. That's 20. 10 times 45 is 450. So 450 and 150 is 600. That's 620 is BY times 25 feet. So therefore, BY is positive 24.8. Did I do that right? Yeah. What do you think? That's the only complication right there. And it really isn't a complication. Just recognize what you're doing. You're summing moments. Okay? So now we sum forces in the y direction. Now let's handle this like we would any problem. Do I consider AX? No, that's not a force in the y direction. I do consider AY. I do consider the 30 kips. I do consider BY. What about the 20-foot kip moment? Do I consider that? No, it's not a force, or it's not a moment. It's not a force, it's a moment. I need more coffee this morning. I am summing forces in the y direction. That's not a force in the y direction. That is a moment. It doesn't belong here. But did I forget something? 10 kips. So AY plus 24.8 kips is 40 kips. And what is that? Is that 16.2? 15.2. Everybody else get that? Yeah. And that's up, and there we go. That's it. And remember, whenever you indicate your final answer on the homework, I want to see the magnitude and the direction. So AX is 0, AY is 15.2 kips acting upwards, BY is 24.8 kips acting upwards. So let me take a step back and see if this was complicated. Was this bad?
No.
I would hope it's pretty straightforward, yes.
How is it possible to have a concentrated moment where there's not a vertical support?
So the idea is to go, we're talking about something like this. The idea is that there's something framing into the structure at that point that's causing the twist.
Yep.
The other thing that I do want you to get used to again is that there's going to be scenarios where there actually isn't a concentrated moment there in the real world, like there's nothing there, but we end up needing to be able to analyze for a concentrated moment to compute things like deflections and deformations. That's going to happen. So. This is good stuff, though. I like this. Any other questions? Okay, this is good. All right, let's do our next one. Now, this next one is our first foray into dealing with cantilever beams. I'll tell you, I think these are among the easiest problems that we do. And one of the cool things about cantilever beams is that simple supports, I think there is at least a modicum of strategy that is applied when computing reactions. So for example, we always say we're going to sum moments before we sum forces in the y direction, right? Because we always, sum moments, let's say at A to determine the reaction at B. There's a strategy there. Whereas for cantilever beams, the strategy doesn't really matter. You can sort of do it in whatever order that you want, and you will more often than not get the right answer with the same amount of ease. And so cantilever beams are easier from a strategic perspective. Now, so the first thing I want to do is I want to indicate the unknown reactions at A, okay? And in this case, there are 3 of them, okay? We have we have AY, we have AX, and then we have a third reaction, which is a concentrated moment, okay? All right. What I typically do is, first off, you have to assume a direction, okay? So I'm going to assume that this is counterclockwise, okay? And you'll get, again, the more problems that you do, the better that you get at assuming this. But I think this is a pretty straightforward assumption. If you look at point A, all of these loads are going to want to rotate the beam in a clockwise fashion. So we need a moment in a counterclockwise fashion to resist it, okay? Now, as for what I call that reaction, I tend to just call it like MA. That's kind of what I call it. You could call it A sub M, whatever you want. I call it MA. I think just keep it simple. But yeah, so those are our 3 reactions. Is there anything else we should deal with now? How about that incline load? Let's take that incline load and let's split it up into X and Y components, something that we should be a little bit more comfortable with after our last assignment. So we're going to take this and do that. The load is being pointed downwards and to the left, so the components need to be down and to the left. This triangle is a 3, 4, 5 triangle, right? So what we do for each of these components, so this is 10 kips times something over 5. This is 10 kips times something over 5. And if we're dealing with loads, we just take the slope ratio indices and match them. So the vertical is 4, the horizontal is 3. So this is 4, and this is 3. And over here, if I have 4/5 of 10, that's 8 kips, and this is 6 kips. Again, if my handwriting is horrible, tell me and I will fix it. It'll ruin my day. trying to tell a few dad jokes there. My goodness. Okay. So the beauty of, again, the beauty of a cantilever beam is it really doesn't matter what order that you do it in. So you can do sum of moments first. You can do sum of forces in the y direction first, and you'll get the answer every time. I'm just going to do it in order. So we're going to sum forces in the x direction. However, I have, especially when you have inclined loads, I have found that it is important to just do them all formally. So we're going to do everything to the left and everything to the right. So I have AX acting to the right. And to the left, I have 6 kips. So that means that AX is in fact 6 kips to the right, as I assumed. I assumed that AX was 6 kips to the right, and I am correct in that assumption. For summing forces in the y direction, okay, so to sum forces in the y direction, all right, so what we'll do is we'll say everything going up and then set that equal to everything going down. So I have AY going up, and then I have 8 kips and 20 kips going down. So AY is positive 28. Again, I think cantilever beams are pretty easy analytically. So far, so good? All right. Now, for summing moments, we do need to select a location about which to sum those moments. And what I'm going to do is I'm going to select the point A. Okay, so I am going to select point A. So we're going to sum moments about support A. You could pick any point that you want. It doesn't matter. I just tend to pick support A because I think it's easier to deal with. If I'm at support A, do I need to consider AX? No. Do I need to consider AY? No. But I do need to consider the moment reaction at A. And I have that moment reaction drawn in this fashion, so I'm just going to list that over there. What is the moment arm? There isn't one. It's a moment. We're summing moments. So do not say MA times some distance. Just throw MA in the table. Okay? What we do need to consider are the other applied moments. Okay? So what do we have? We have 8 times, what, 10? 20 times 20. Did I consider that right? So all right, so 8 times 10 is 80. That's 400. So that's 480. Or it kind of looks like a 9. If I can do that better. That's a little better. And then in terms of the direction, I have assumed that it is acting this way. I got the correct or the positive answer, which means that my assumption is correct. And so the direction of that moment is like that. So what's my answer? AX is 6 kips to the right. AY, 28 kips up. MA is 480, I skipped a digit there, 80 foot kips, and that is acting in that direction. Remember, moments are vectors too. They have a magnitude and a direction. The direction, though, is either going to be clockwise or counterclockwise. We're going to talk a little bit about the next lecture, but then we'll probably have to call it a little early today. So, what do you think?
Easy peasy.
Easy peasy? All right, let me pull up a little bit about what we're going to do in the next lecture, because the next example that we're going to do on Friday is going to take a while. And I want to make sure that we're all clear on how we're going to go about that. So, all right. So I want to talk a little bit about this. So I want to talk about internal hinges and releases, and what is among the most valuable tool to a structural engineer, to a structural analyst, and that is the ability to cut a section. We're going to be doing this all the time in this class, and I want to make sure that you're comfortable with it, okay? So I want to say a few things about internal hinges. We're not going to do this example today because it's going to take a while, but we'll get into it. So up until now, we've handled just about every boundary condition and load that we can consider. Concentrated moments, incline loads, all this, pin boundary conditions, rollers, fixed, you name it. The last thing that we haven't dealt with is an internal release. And I talked about this, I believe, during the first real lecture. I think it was lecture 2, when we talked about classifying structures. And what we said about internal releases is that internal releases provide us an additional known to the problem, right? So whenever we compute support reactions, we've got at least 3 known parameters, 3 known facts. We know that the sum of forces in the x direction is 0, the sum of forces in the y direction is 0, and the sum of moments is 0. But an internal release, and most commonly for us, the most common one we'll deal with are hinges, an internal release provides us a known quantity or a known fact about the structure at a given point. And so a moment release or an internal hinge tells us that the internal moments in a structure at that given point are 0. And we talked about some physical examples of that, like the beam splice that only connects the webs. We talked about pin and hanger connections, etc. But what I want to talk about is how do we use that, okay? So what we do is we break out the secret weapon of a structural engineer, which is a samurai sword or a lightsaber, if you happen to be a sci-fi fan. We've got some engineers in the room, which leads me to believe there's at least a couple people that would prefer the Jedi way of doing things. But what does that mean? Okay, so I go back to some of the discussion that I had in statics. So here's a table, and I'm sitting on this table, okay? And let's say there's somebody in here that doesn't like me very much, and they decide they want to play a trick on me. So they break out their lightsaber, and they cut right through the table right here. What happens to me? I fall down. What happens to their grade? Pretty obvious. But why do I fall down? Why do I fall and hit the floor? It is because inside the table, right here, there are obviously some internal forces that are keeping me stable and uplifted. If you were to take a samurai sword or a lightsaber and cut right through the table, you would be releasing those forces and I would fall down, right? So cutting a section is an analytical tool that we can exploit to determine what are those internal forces inside that point. Because if we understand that, then the next natural step is, well, how thick does this table need to be to adequately support the loads that we're subjecting to? And I'm talking about tables, but as civil engineers, we're going to apply the same logic to buildings and bridges and dams and what have you. Okay, so that's kind of what the goal is. Okay, so cutting a section can be used as an analytical tool to validate answers, to determine internal forces, to determine moment and shear functions, and plot shear and moment diagrams, all sorts of things. Okay. Now, what happens when you cut a section? So, if I have an arbitrary point in a structure, if I have an arbitrary point, and I take that point and I samurai sword or lightsaber through it, and I look at either side, what I develop are, for any arbitrary point, 3 unknown components, right? So I want to first off focus on this. I want to focus on this free body diagram right here. So if I take an arbitrary point in a structure and I samurai sword or lightsaber through it, what I'm going to get is I'm going to get the structure split up into two halves. Like here's the cut, and I've got the structure that's on this side of the cut and the structure on this side of the cut. Now, obviously this act of cutting a section is akin to a philosophical exercise. We're not actually taking the structure and cutting it in half. But if we were to do that, we would be removing from the structure the ability to maintain equilibrium. Because for the structure to maintain equilibrium, there have to be forces inside the structure at that point. And I propose that for two-dimensional structures, there are at most three unknown forces. An unknown force in the x direction, an unknown force in the y direction, and an unknown bending moment. And regardless of which side of the section that you look, numerically you should get the same answer. So if my unknown force in the x direction is 20 kips over here, it will be 20 kips over here as well. Doesn't matter which side of the section that you look, you're going to get the same answer. What is most important to make sure that you're handling appropriately from a bookkeeping perspective are the signs. Okay? Now, if you notice, this is not arbitrary. Look at the actual direction of these arrows and look at the direction of these arrows. What you will find when you do this type of analysis is that you will get equal magnitudes, but you will get opposite directions. So, for example, if we're talking about the forces in the x direction, if you get 20 kips to the right and do a completely separate analysis, you should get 20 kips over here, but it will be 20 kips to the left. Okay? The best example of trying to explain that physically is a tug of war. Okay? If I have a rope and he has a rope at the other end of the rope and we are yanking on it, we are both yanking on it in opposite directions. Even though we're doing the same thing to the rope, we're both taking the rope and applying tension to it. If he's pulling this way and I'm pulling this way, we're achieving the same internal response by applying those loads in opposite directions. Yes?
So it's kind of like how in mechanics of former bodies you talked about the shear stress, all about perspective. On this way, they're pulling this way. Turning one way, look the other way.
Exactly.
It's still the same force.
Exactly. It's just the perspective in which you look at. That's 100% right. Now, what I have here on this diagram, and to be honest, for the diagram that we're highlighting, that we're circling, it doesn't really matter all that much the direction of the arrows that I have drawn. But what I will tell you is that what I have here is I'm drawing everything according to the positive sign convention that we're going to use in this class. So for example, with shears, if you cut a section and look to the left, downward shears are considered positive. If you cut a section and look to the right, upward shears are considered positive. We could very easily flip that. And as structural engineers say, no. Upwards and downwards, that's positive. Like we could do that if we wanted. There's no discernible, we must do it this way. However, we as civil engineers choose this sign convention because it maps very well to the graphical techniques that we're going to use later to draw shear and moment diagrams. So that's why shears downward on the left are positive and upward on the right are positive. It's the reason moments are, counterclockwise positive over here, clockwise positive over here. As for the forces in the x direction, the reason why this is positive and this is positive is that these correspond to tension. Tension tends to make a member longer, so we tend to treat axial loads that are in tension analytically as positives. That's why the forces are drawn the way they are. Honestly, right now, the directions of those arrows don't matter all that much as long as you recognize that they're equal and opposite. Later on, though, the direction really, really will matter. Okay? Everybody with me so far? Okay. This is what happens when you cut a section through an arbitrary point in the structure, but I'm talking about hinges. What happens when you cut a section through a hinge? What is the difference between cutting a structure through an arbitrary point and cutting a structure through a hinge? Well, through the hinge, we don't get 3 unknown components, we get 2. This is a hinge. A hinge is an internal release. The whole point of having the hinge there is we know one of those internal responses. What is one of those internal responses? The sum of moments is 0. Okay? So what we're going to do when we handle problems with internal hinges is we are going to cut sections through those hinges. And I can some moments right here and not have to consider those internal responses and determine everything else. So that's what those internal hinges are going to do for us. Internal hinges are going to show up in a couple different contexts. When we start drawing shear and moment diagrams, we're going to have problems with internal hinges. And when we look at the moment diagram, and we look at the moment diagram where the hinge is, by golly gosh gee, the moment diagram is going to be 0 at the hinge. So we are going to see this pop up in multiple contexts in the not too distant future. So just be aware of that. Now, I wanted to make sure that you had the sign convention for internal forces a little bit more laid out in a less cluttered fashion, as it were. So this is what positive axial forces are going to look like when we do our truss analysis. When in doubt, we're going to assume that our truss members are in tension, so we're going to assume that they look like this, so that if we get a negative answer, that means they're in compression. This is also how we're going to handle 2x2 systems of truss analysis, which is something we're going to deal with when we start doing method of joints sort of revisited. These are what positive internal shear forces look like, and these are what positive internal moment forces look like. So this is the same thing that you just saw, just a little bit decluttered. Again, I'll tell you, for the purposes of support reactions, it's not going to matter a whole lot right now, but when we get into later analyses, they're going to matter a whole lot. So just make sure that you are aware and comfortable with these. So this is going to be the problem that we tackle. We're going to tackle this on Friday. We're not going to do this today. We're going to see a problem with handling this structure the way that we've handled all the others. And you'll see when we get into this why cutting a section is necessary, why we really can't go about this problem with the tools that we developed so far without cutting a section. Okay? Make sense? So this is what we're going to deal with on Friday. You all are getting 7 minutes back. That's all I got. I will see you all on Friday.